All right, hello pre-calculus students. Wanted to give you a feel for why the cofunction identities are the way they are. That helps memorize them. And also I'm showing you a few quick sketches you can make to remind yourself of what they are exactly. So to understand the cofunction identities, you actually have to understand a little bit of the history of where we got the name of the sine of an angle and the cosine of an angle in the first place. Well, first of all, sinus in Latin for the sinus of an angle was a complete mistranslation of an Arabic translation of some Greek, or finally getting back to the Sanskrit. In the Sanskrit, the chord of an angle was described as being the length of the line segment from A to B in a bow and arrow. So imagine this is the bow and there's an arrow across here. How far, and this is the string that's been pulled back by the finger, right, of the person shooting the arrow. So the angle theta generates a certain length of that bent bow, right? And so in Sanskrit, whatever the word for the chord of the angle, that was that length AB. Well, somehow it got translated into one form of Arabic, to a correct form of the Arabic, I assume originally, but by the time some Latin scholars got to it, they mistranslated, and I think they also kind of misunderstood what was going on. So the word sinus is pocket or curve. So I think that the person who was translating thought that it was the length of that arc, AB. And that's what they were calling sinus of the angle. Move on a couple hundred years, they realized they didn't need to look at that whole central angle there so much as half of it. And so then people are referring to, by the time of the Greeks, as the sine of an angle is the length, they're calling it the sine, as the length of this chord, maybe later than Greek, sorry, Romans, Latin, yeah. They're referring to the length of the chord opposite an angle in a right triangle. They're calling that the sinus of theta. And then in English that became the sine of theta, that's what we call it. So that describes how we got in a right triangle where the hypotenuse is 1, we can say that length of the side opposite, the leg opposite the angle theta in that right triangle is the sine of theta, the length of the side across from that angle theta. Okay? Now, of course, in every right triangle, you not only have theta, but its complement, which we symbolize by theta prime. So theta prime is sitting right here. What's the length of the side opposite it? So the side opposite being, the length of the side opposite is the sine of that angle, so the sine of the complement of theta. There was a while there, we're progressing in hundreds of years here, where it was the sine of the complement of theta, or the sine co of theta. Finally, that got shortened to just 3 letters, maybe by the people who make the calculators, who knows, cosine of theta, or just cos theta. Okay, so what is the cosine of an angle? It is the length of the side opposite the complement, the length of the side across from the complement. Okay, so look what that gives you now when we go into, we have this coordinatized system, right? Descartes coordinatized everything. And so you could say now that in the unit circle, in the triangle OPQ, where we have the hypotenuse is equal to 1, right? The length of the side PQ is the sine of theta, that's the length of the side opposite of theta. And from, let's see, if we throw in another letter V here, V sub theta, so we take the usual OPQRSTU V, now I'm up to V. So if you project P sub theta over here onto the y-axis, that's P sub theta, excuse me, you get V sub theta, so that's right here, this point right here. So grab that little rectangle, OQPV, OQPV, put it over here. Again, assuming the hypotenuse is 1, the length of this side is what we're calling the sine of theta, the length of the side opposite. There's theta prime, so the length of the complement of theta, the cosine of theta, is right here. But we also have another copy of the complement. The complement of theta is right here. The length of the side across from it is the sine of theta prime, right there. Okay? If in OPQ you say, right, so sine of theta is the length of the side opposite from theta, and cosine of theta, well, it turns out to just be the length of the side adjacent to theta. You can not refer to theta prime by just saying the length of this side is the length of the side adjacent to theta, right? There's theta. The side adjacent to it is the cosine of theta when this hypotenuse is 1. All right. So then, as a little side thing, being able to, given a right triangle that is similar to our OP theta, Q theta, you could say, because these two triangles, OP theta, Q theta, are similar, just want to make sure you can see the whole screen there, and getting rid of the glare, voila. Okay, so if the lengths of the side of OPQ are cosine theta is the length of the side adjacent, the length of the hypotenuse is 1, sine of theta is the length of PQ, length of the side opposite from theta. By similarity of this triangle with theta here to any right triangle with theta there, even if this is 100 miles and that's 75 miles and that's 100 and some other miles, you could use, of course, Pythagorean theorem to get that exactly, but no matter what scale, if you have a triangle ABC, whose sides are length little a, little b, little c, you've seen that in terms of the Pythagorean theorem. If the angle theta is here at B, then the side next to it, the adjacent side, is BC, or little a, because that's opposite of A. And little b, which is the side opposite of B, is considered to be the opposite side from theta. By using the similarity of this triangle with that one, no matter the lengths of this hypotenuse or adjacent or the opposite side, we can say that the sine of theta is equal to the ratio of the opposite to the hypotenuse, the cosine is equal to the ratio of the adjacent to the hypotenuse, and the tangent of theta is equal to, well, tangent of theta, back up here. Remember, similarity of triangles gave us the tangent of theta was always the ratio of the sine to the cosine. That's our definition. And so it's true in this right triangle that you could say, therefore, the tangent of theta is the ratio of the opposite side to the adjacent side, using similarity of triangles and that definition of the tangent. Well, this might be, in fact, how you first learned anything about trigonometry. Someone writing a textbook in Indiana in the 1870s noticed that they could make a nice little mnemonic device, SOH-CAH-TOA, or SOH-CAH-TOA. I just want to point out that's very recent, and unfortunately for a lot of people who've had some trig, that is all they ever remember about trigonometry is SOH-CAH-TOA. That is not enough to do well in a calculus course. That can only barely get you started. So I just want to connect the dots. If SOH-CAH-TOA is the first thing you learned about trigonometry, I just want you to realize this just a kind of little side street. All right, so back to the cofunctions. Looking at cosine and sine as functions of theta. So where did this name cosine of theta come from? Because it is the sine of the complement of an angle. How do you say the complement of an acute angle when you were talking radians? It's the sine of pi over 2 minus theta. That's the complement of theta, right? If here's theta, There's theta prime. They add up to pi over 2, that right angle. The sine of theta is equal to the complement of the sine of the complement. Because remember what the cosine means. The cosine means the sine of the complement. So this is saying, oh, the sine of theta is the sine of the complement of theta. That's just a description, really, of what the word cosine means. Okay? So, but in any case, you will see an equation like this and be told, and in our book as well, oh, that's a cofunction identity. Memorize that. You can work out from a picture like this what's going on between the sine of a complement of an angle and the cosine of that angle. So that's why I'm presenting this video. And the sine of theta, of course, is equal to the cosine of the complement of the angle. So using those two, you can come up with identities for the tangent of the complement. You don't have to memorize two more identities. You just go back into what's your definition of the tangent in this class. The tangent of some angle is the sine of that angle over the cosine of that angle. If you have pi over 2 minus theta in each of those slots, whatever, right? That's true for our definition of the tangent. What is the sine of the complement? Oh, that's the cosine. That's what they mean by the cosine. What is the cosine of the co, double up, and just give you the sine. Right? So that's why, now that's the cosine over the sine, which we proved using similarity of triangles, let's see, OUT, with a triangle POQ, that the cotangent of theta was always equal to the cosine over the sine. So what do we have here? The tangent of the complement is the tangent of the complement, or the cotangent. Similarly with the secant, or the cosecant, you don't have to memorize stuff. To derive this fourth cofunction identity, just go to your definition of the secant, which should be, which we proved using similarity of triangles, the secant of blah is always equal to 1 over the cosine of blah. You just happen to have pi over 2 minus theta in there for blah. Okay, now what's the complement of theta? Oh, that's the sine of theta. So rederiving these two so that you can then get any of the other cofunction identities is probably what you're going to end up doing in the middle of some calculus exam in the future. Okay. Trying to memorize all that along with 796 other identities, not the way to go. Just memorize a few things, be able to derive the rest.